Hello, diamonds in the rough. So in this video, we're gonna continue with decision boundary, and I think I did some typo back there, so I'm gonna correct that. And also, we'll moving forward with feature engineering, which is a really exciting thing, and also stepping into neural network for the first time. You will see the glimpse of neural network for the first time. And what is beautiful about this video is gonna be that when I was learning decision boundary, it was very hard for me back in 2017 when I was going through entry course. I had such a hard time understanding decision boundary. I think that thing could have been have better. So I'm continuing a better version of it than Andrew sir. So let's begin with that. So as you know, we have our data which we have been following for quite a long time, and we have a predict function, and we have predict function made out of sigmoid values because we know that for some data points in classification, basically in classification data set, a straight line will not fit the data and losses will be too much. So we need to have some kind of curve shape. So this straight line will not, so we will try to curve this straight line so that it could fit the data, right? And just to just to just to clear it, when you try to fit this data, what do we say, you try to fit it like this. Yeah. When you try to fit the data over here with a straight line, if I just continue with my normal method, like if I just continue like how simple loss RMSE, root mean square error method, if I continue with that, probably we'll find a line which separate is over here. I has this confusion that this line might be like this, but no. The line, if I just use root mean square, this line will be somewhere here, and that will be our like model. That theta will be my model for that slope or intercept. But it is not gonna cover these points, right? So we curve that straight line into a S shape from there only, right? And that S shaped line we got because of this non-linear function sigmoid, and this S shape, this will fit the line, and the model will be quite good. And if we just dissect this function, which is combination of linear function and non-linear function, this is the non-linear part, and this is the linear. If we just plot this linear part, it will be somewhere over here. And if I didn't had sigmoid, still that line would be somewhere here, right? That will be the beauty of it. Like that will be the best line, segregating that this inside line over here. This line is basically, you can think as a decision boundary. What decision boundary doing? It's segregating into two parts. So all of the data points which belongs to class 0 is after this point, and everything is after this. So this is a good segregation point. That's why this sigmoid work. That's why everything is work. So that is the decision boundary. I hope you got. In the last part, I just mentioned you wrong. That was the cross diagonal line, which was not the case. I think the cross diagonal line would come if I do it without sigmoid, because that time that's the cross diagonal line, I think closest. I'm still confused, but I think that will be the closest one. Uh, so this is decision boundary, and moving forward, for which we came over here, the main important thing is feature engineering. So there is a new some set of example. I added few more data point in that data set, and now if I plot this thing, this is a little weird data set. Why it is weird? That previous one was, we already could see data was well segregated, but over here you can see we have a point which is quite far away from its group, and this one is also. So the line which is segregating is somewhere over here, and and this one is going beyond that. And this S sharp sigmoid will also not fit this line. This straight line will never do, but S shape will never do. Why is that? Not S shape. S shape will also not, because a good S shape wire could go like this. A line could like this, and it will lose this point and this point. Or probably a Z shape function would work, but we don't have a Z shape. Maybe you can invent it, but we don't have this Z shape function yet right now. So what do we cannot change the function. We don't have another function. What we can do? We could probably change the data we have. What if I apply some transformation at it, some kind of scaling, some kind of transformation, and it does work, right? And it helps. Maybe multiply x1 with some value, or x2 with some value, divide with, or plus with some value, right? What if I could do something with that and it solves the problem? Exactly what that we're gonna do is, take these x values, x1 y values, and create a new feature which will be multiplying both of them, sorry, adding both of them and subtracting both of them. And if I do that, I will be have new table with new x1 x2 values, right? That will be combination of both of them, and these guys will be they will look different when we plot different. There might be some improvement, so let's see that. Yeah, we will continue with that. uh, and not only with that, right? Let's say even doing that we don't got the answer, maybe we could have a version of them same addition and subtraction, we multiply some weight to it, like 3 4 something, like just to make it scalable. Like when we do scaling, we multiply with something, right? Divides, add, something we do. So just we do, let's say we create a feature where the basically the new feature is multiplication of 3 and then multiplication of 4 with other feature and combining them, something like this. And then we could have more better feature what we had initially. So these are the way to create new features, and just new features, and then they probably will have very segregated it, and there I could have done some fitting to it, model fitting to it. So now let's plot that data, like after feature engineering, right? The second one or first one, you can think like what happens is that it actually when you plot it, it actually will segregate it. So data points like will look something because of multiplication something, they become bigger or something like this. And then now it's looks segregate. So a sigmoid kind of model will definitely fit on it. So we will draw that, we'll continue with that, and we will probably have a sigmoid function which could fit on this thing. uh, just to inform you, these example which I have picked right now, these are random. This will probably not make sense when you try to recreate it. I was being lazy from my part. I could have come up with right numbers which would have fit, but there is definitely exist some data set where these things will be happening. So if you try to replicate it, probably that is not gonna work, because this is imaginary numbers I'm taking, just proof of concept, right? But there will be definitely, I will be giving an example with a real data set probably in the next video or something like this, but not this one. But this, the idea is same, the same working will be happening whatever I'm trying to tell you. So now it is fitting because of the feature engineering. But there is a question which I want to ask it. When we created feature, how would he know that I have to plus between them or subtract between them to create new feature, or have to multiply a weight to it, like a 4, 3, 5, 6, whatever, -5, -6? How we decide? In machine learning, we don't decide anything. We don't take any decision making should be on the data should decide. It should add or something like this. So this is not a perfect algorithm. A perfect machine learning algorithm is something which we don't do the decision making. Let the data decide whatever do, right? We just built our magical algorithm and let data decide to rule it. Like we create a semi formidable kind of algorithm, and this algorithm solidify itself with data, right? That is goal, that is we want to do. So what we can do, we cannot have our own mind telling it multiply with 3 or 4, right? Instead what we'll do, we will let model decide, the data decide what kind of weight we have now. So what we can do is we could create a features like this. We called it hidden features, like same the way we feature, but instead of telling what exact number, we'll replace with sorry, see w1 over here, w2 is basically I'm talking about theta 0, w12 is basically theta 1, and w21 is basically theta 2, and then w22 will be basically theta 3, right? This is I'm talking about. So we can create same features, but this time instead of giving them a solid number or something, I will just give them no random weight, just a variable, what we call it, a placeholder kind of thing, right? And it could be negative. If negative, then it becomes a negative, then doesn't become a sum. If there is any of these values negative, then it's become a subtraction. So we created this new features, hidden features, and basically we don't know what we are multiplying to it. It will be random. Just like how we can figure out theta through the loss function, same way we want to figure out what kind of weights we're going to multiply these features to create new features. So we'll create a kind of graph, kind of. It look fancy, but while coding it, we'll probably doing with some mathematical formula. But just for explanation, I'm making graphs. You don't have to make graphs while doing that. And this will be like this. And once we have this new feature, now it becomes the same thing which we did with Pareto logistic regression. Now it becomes new x1, new x2, and then we have these two thetas multiplying to h and then adding them together, and that becomes y. That will become prediction, and then we have to subtract with actual prediction. And when we do that, we'll probably know about loss. Initially, these all thetas will be random, and with random we will have a very high loss, and then we eventually figure out the thetas. Let's see that forward, how we can do that. So next slide, probably we have that data over here, and we have this predict function. As you can see, there is a changes in predict function. We are not multiplying theta values with x1 x2. Instead of, we have something hidden feature h, which I'm putting a place and holder theta 0 and theta 1, and over here theta 2. We don't know it. Randomly we will have random values. So probably the h1 h2 will have some random bullshit coming out of it. And once we have this predict function, we will have a loss function, so that we know that how better my initial guess random theta as well, and we probably know that theta is the loss is very high. How can we optimize that theta? I just expanded a log loss over here. You can see there's a log, there is a sigmoid, then this h values which I multiplied over here, right? And how this log function created, it create over each row over here. Each row will go into the prediction, come up with a prediction and loss function, and each row will have accumulated its losses, and that will be summed up. So 8 examples. When we do that, we'll have loss. Now our goal is to optimize this theta, and this theta will start with theta 4 and theta 5. These are very simple, right, that we have done previously. So how we will optimize this theta 4 and 5? That will be basically whatever the derivative, the slope at that point, right? There is a slope at that point, and slope is basically the derivative loss function at that point with respect to theta. Slope over there will tell, hey, you are going in the right direction. If it is a high slope, then you are probably in the wrong direction, or negative as well. So if you find the slope over here and solve it, to find the derivative at this point, you will probably solve it. Basically that will become actual minus predicted value, h1 value, right? Previously when we were only dealing with without feature, there was x1, so x values were multiplied. Basically if I am taking this example, these all example eventually sum up, but if I have to pick particularly this, I will multiplying with 29. When this was the before the hidden feature, 29 will be multiplied over here. Sorry, in this example, if theta 1 was the problem, then 1 will be multiplied. If theta 2 was there, 29 would have multiplied. But now we have h, and h1 comes from some multiplication. So we will not multiply with 29. Instead, we will pass this 29 over here and 1 over here, and have this random theta, and then sum up something. So this is h1 is outcome of some input x, right? So that will multiply. That we got it from derivatives, and if we follow that, we update we use the update method, and eventually after so many iteration, we'll probably find the right theta values which will fit the second part of the theta. Like if you remember our network back in the previous example, this part of theta will solve. But this h1 is mixed function, right? But we have also to figure out what the feature engineering weights we need to find. So same way, we'll find derivative of those things with respect to theta 0, theta 1, and then it becomes like a chain function. Like previously it was a chain function. Log y actual was the function of sigmoid, then the function inside sigmoid we have another function. Now this even h is a function, so h will be replaced by another function, so it's became a chain function, right? And when we do chain function derivative, we have same thing like as derivative, but also the result will have a derivative of this point. When we have derivative of some chaining function, so whatever the function derivative has, and then whatever inside the function, you do have the derivative of that value as and multiply with this. So when we break down h is made from x values and theta value. Theta values are basically constant values, so they will not take a lot of part in derivative. But when we solve it, the x will come out, and when we this x is multiplied, the respective x, sometime it will be x1, sometime it will be x2, sometime x2. So according to those thetas, different x values came. So now when we have to update the thetas over here, we can same way, just like we updated these thetas, this one and this one, same way we can update these ones, but they will be function of functions, right? The derivative will be function of functions. And when we do that, so basically going a next level, next layer inside that. And when you iterate all of them together, like we'll start with random thetas, one will be helping for the features, one will for fitting the model. All of them gradually will move in the direction where we have the golden weights, golden thetas, where our losses will be limited, and we will beautifully constructed a model on a complicated data without doing feature engineering even, right? So that is the power of neural network. So that is the, I think, the synapses of, like, this is the beginning of neural network. These hidden features are called neural network. This is like this idea how we can have created these features and this graphs. This comes from the neurons of our brain. So that way we don't have to decide what types of features we have to. So now this example, by the way, these are dummy data, these are not actual data, so if you replicate, probably not will happen, but the ideas will be concrete, they will follow in every kind of data set. And one thing I was telling that not only simple features like x plus or x2 something, like there will be a requirement of x square. Sometimes you'll require a non-linear function. How this simple looking neurons will figure out how to have inside that sigmoid function non-linear function like x square, x cube, or something like this, right? So that we're gonna probably watch in next video, and I'm pretty excited that you guys will be there to watch that. I think nobody has explained that. I think you will search on video, you will not find nobody explaining how the square functions are made inside these neurons or something like that. These are the simple ones, looked very linear, was able to do simply with two neurons, like two hidden features. But in future, uh, we could have a feature over here like basically squaring x2, and you can square. Normal feature engineering, manually you can come up with x square feature over here and do it. But how can we get x square feature in a network, right? How we can do that? So that I'm going to teach you. Also, one thing I didn't tell you to, just maybe I thought maybe you guys will get confused, or whenever we find features and when we do features, we don't replace with older features, we add it, we concatenate. Basically we'll have four features over there. This will be the raw features, and the new features whatever we made, x3 x4, and then we'll pass it on. This is I'm telling before this hidden neuron part. Like if I have to manually create features, even though if I create features, I will not pass the new ones, I'll send all. So machine learning always best when you give more data. So whatever raw form is it, they're going to also help somewhere in the modeling. So never hesitate to send more data to a model, even if it goes to multiple dimensions. So I hope you have got a lot of clarity from this, and I want you to subscribe that, because I want you to be there in the next part that will absolutely blow your mind, and I will give you real values so that you can practice this kind of thing, and it will be more visual than this one. So hope to see you on. Bye bye.